Hello grade 11s, it is physical science and my name is Gillian. We are going to consolidate now our knowledge on Sir Isaac Newton's gravitational law, and that is the universal law of gravitation, which talks about the force between two bodies in the universe and how they attract one another. It is directly proportional to the product of the mass of those two objects and inversely proportional to the square of the radius between them. Okay, so now we've got to take that knowledge with the equation and we have got to apply it to questions. So we've got a couple of practice questions we're going to go through. You can go through them with me, have a piece of paper and a pen with you and see if you can do this along with me. Right. So our first question is, the acceleration due to gravity on planet X is that amount, 2.7 meters per second squared. The radius of the planet is 1/3 of the radius of the Earth. Now, when we read that, we tend to panic a little bit, because this is a question about ratios. They're not giving us actual values, and so we have to work around it. But we are going to, and I'll show you how. So let's not panic too much. The first question that they're asking us is to explain the difference between weight and mass. Now, in our society, we often confuse the word weight with mass in our everyday conversation. So we think when we say, what is your weight, that we're asking, what are you measuring on the scale? But actually weight in the science world is talking about the force with which you are attracted to the Earth. That's weight. Mass is the total matter that's in your body. So let's start with mass and write it down. So mass is the amount of matter in a body. So that's actually what everyday people are asking you when they're asking you about your weight. They're asking you how much matter is actually in your body. And there's really not much you could do about that. Unless you remove a limb or something. So the mass is about the amount of matter in the actual body. So what is weight? Weight is the force with which a body is attracted to the Earth. It's a big difference because we now have gravitational acceleration involved in that. And so this is the formula for it, which you've seen before. So the mass of the body times gravitational acceleration on Earth is 9.8 meters per second squared. And of course your weight would change if you're on the moon or if you're on a different planet. The next question now is asking us to calculate the mass of this planet X. Okay, so before we get confused, let's write down everything that we know. So they're telling us that the gravitational acceleration, so the acceleration due to gravity is, for this particular planet, is 2.7 meters per second, and it should be squared. Okay, the radius of this planet is 1/3 of the radius of Earth. So what is the radius of Earth? So we can get that from our data sheet, and it is 6.38 times 10 to the 6, and I don't know this off by heart. I have written it down in front of me so that I can give it to you. What else do we know? we do know that we have this formula from Newton about universal gravitation. And we also know from his second law that Fg is equal to mass times gravitational acceleration. So if we substitute that in, so mg is equal to the constant, mass 1, mass 2, divided by r squared, we can see that we can cancel out that mass. And so we end up with a formula that looks like this. G, gravitational acceleration, is equal to the mass of the planet X that we're looking for, times the constant, divided by a third. Now look there, there's the third of the radius of Earth. Now all we need to do is we need to substitute in and work with that third. So that third's not going to, should not confuse you too much. We are going to substitute in 2.7 for gravitational acceleration. G we get from our data sheet, so it's 6,67 times 10 to the minus 11. What are we trying to find? We're trying to find the mass of this planet X. Okay, now what are we going to do? Well, we are going to say the radius of Earth, which we do know is 6,38 times 10 to the power of 6. We are going to times it by a third. Why? Because they tell me that this planet X has got a radius which is a third of the Earth's radius. So if we times the radius of the Earth by a third, we're going to get the radius of planet X. Once we've done that, we are going to square, remember that square that we often forget, that whole amount of the radius. And if we work through our calculations, we can rework this calculation so that the mass of planet X is the subject of the formula, and we get this. So 2,7 times 4,523 times 10 to the 12 divided by 6,67 times 10 to the minus 11. And if we calculate that all out, we get an answer of 1,83 times 10 to the 23 kilograms. Now, let's check. Because we've got this answer, how do we know that it is correct? We are thinking, if we look at the gravitational acceleration, it is quite small, quite a bit smaller than Earth's, because we know that G, gravitational acceleration for Earth, is 9,8 meters per second squared. Okay, we've been told that the radius of the Earth, a third of that is going to give us the radius for planet X. So we are, in our minds, we're thinking, well, this planet X must have then a smaller mass than Earth. So we see that the mass of Earth from our data sheet is 5,98 times 10 to the 24 kilograms. Is it smaller? Yes, absolutely, it's smaller. That's the answer that we should be getting. We're happy with that. Okay, the next question. Determine the factor by which the weight of an object on planet X will differ from the weight of the same object on Earth. Oh, weight. So again, we're talking about weight. Remember, it's F. G is equal to mg. Now, we don't have the mass of this object. The only thing that we have to compare is the gravitational acceleration. So I've drawn myself a picture here. I find pictures are very useful in figuring out problems. So I've drawn planet X as I see it, and I've drawn Earth because now I'm thinking Earth is bigger, the radius of planet X is a third of the radius of planet Earth. We can see that our gravitational acceleration is also less on planet X compared to that of Earth. So I've drawn planet X smaller than planet Earth. Right. I don't have mass to compare, so I can only really then compare the gravitational acceleration. So this is what I'm going to do. I'm actually going to form a ratio. I'm going to divide the one by the other. So 9.8 meters per second squared divided by 2.7 meters per second squared. So that's the ratio. It's saying how many parts to how many parts. And the answer here, when I do this calculation, is 3.63. Now, there is no units with this because it is a ratio. It is a relationship. And so planet X is going to be 3.63 times smaller. 3.63 times smaller than planet Earth. So what does that mean? It means that the weight of the object is going to be 3.63 times smaller than the weight on planet Earth. So that's our answer. That's a beautiful ratio question. Grade 11s, we need to take a quick break. When we come back, we're going to solve some more problems. Welcome back, grade 11s. Let's dive straight into this. So I have this terribly drawn picture. I know it looks like a butterfly of some sort, but it is actually a satellite. A man on Earth weighs 720 newtons. What will be the force of gravity on him in a satellite? Okay, he's in a satellite now, orbiting the Earth at a distance twice that of the Earth's radius above the Earth's surface. Oh, okay, let's not freak out too much. Let's write down what we know. So we know that this man's force on Earth is 720 Newton. We know that he is now in a satellite. Here's the satellite. And that satellite is 2 times the radius of the Earth. Okay, so we know what the radius of the Earth is. I'm just going to call it R for now. So R, the radius of the Earth, is 6.38 times 10 to the 6 meters, and that is from the data sheet. Okay, we also know what G is. There we go, we've been given G. Well, it's written there. G is 9.8 meters per second squared. That we also get from our data sheet. Right. From Newton's law of universal gravitation, we have the formula. There we go. Now, this force that he experiences on Earth, the 720 Newton, that is going to be what we get from this formula that I've outlined here. Can you see it there? That's going to be the same as 720 newtons. What about the radius? It says here that the radius is twice that of the Earth. So that's where the 2 comes from. We've said 2 times the radius of the Earth. Okay, but G, m1 times m of Earth, mass of Earth, divided by r squared is 720 newtons. What is the difference here? Well, F equals then half of the force on Earth? I know what that is. They've given it to me. So I'm going to say 720 divided by 2, and my answer here, as I'm running out of space a little bit, is 360 Newton. How easy was that? So all we have to do is just apply a little bit of thinking and not panic too much when we see these ratio questions. Our next problem. The gravitational force on a probe called Curiosity on the surface of Mars is so much. The mass of the Curiosity is 900 kilogram. Oh, state Newton's law of universal gravitation. That is easy marks. Let's do this. So every body or object in the universe exerts a force of attraction on every other body Now, this is the important bit. That is directly proportional to what? To the product, very important, product of their masses and what else? And inversely proportional to the square of their distance or radius apart. Great. Let's move on. Calculate the gravitational acceleration on Mars. Wow. We already know that Fg is equal to ma. Fg, they've given us, they've told us that the gravitational force is that. It is 3,338 newtons. What is the mass of this probe, Curiosity, or buggy? It is 900 kilograms. What do I have to find out? I've got to find out this gravitational acceleration. Let's just make that into a g. Right, I just turn my equation around and I find that the gravitational acceleration on Mars is 3,71 meters per second squared. That's quite a small amount, isn't it? Compared to Earth, because Earth is 9.8 meters per second squared. Calculate the weight of Curiosity on Earth. This is another easy one. Let's have a look at it. So weight, so the other one is force of gravity, is equal to mass times gravitational acceleration. So we want to find out the weight. That's what weight is. It's the force with which the Earth attracts a body towards its center. The mass of Curiosity is 900. The gravitational acceleration on Earth is 9,8 meters per second squared. And that's a simple calculation. And we end up with an answer of 8,820 Newton. Easy. Next question. Two satellites are orbiting the Earth and are situated on opposite sides of the Earth. Satellite A has a mass of 3,800 kilograms. Satellite B has a mass of 4,500 kilograms. Satellite A is at a height of this much, 25,000 kilometers above the surface of the Earth. So I want to draw a diagram because that makes me happy, and I can then understand what's going on. So here's Earth. So I've got satellite, I'm going to draw satellite A over here, my weird looking bug. Oh, that looks better. That's a better looking satellite. Okay, let's call that A. And A I know is 3,800 kilograms, and it is a distance of 25,000 kilometers from Earth's surface. Okay, from Earth's surface. So B is going to be somewhere else. I'm not worried too much about B because they're not asking me. The first question is not about B. So let's read. Calculate the force between the Earth and satellite A. Okay, so we've got F is equal to G M1 M2 divided by R squared. They want to know the force. What is the force? So I need to find F. Do I have the other bits of information? Well, let's see. G is the constant times 10 to the minus 11. Do I have the mass of the satellite? I do. It is 3,800 kg, kilograms. Do I have mass of Earth? Yes, I can find the mass of Earth. Mass of Earth is found on my data sheet. So 5,98 times 10 to the 24 kilograms. What about the radius? Now, this is the tricky part. I'm going to change color so we can see. Here is the radius of Earth. That's the radius of Earth. So the distance from the center of Earth to the satellite is going to be the radius of Earth plus this amount that the satellite is floating above Earth. So the radius of Earth is from the data sheet times 10 to the 6 plus, now I have to change the kilometers into meters, remember, so I'm going to times by 1,000, so this would be 25 times 10 to the 6 meters. I add those together, and what do I have to do? I have to square them. Right, so once I have used my calculator, my scientific calculator, I've popped all these values in. Don't forget to square the total distance between the center of Earth with the satellite, the difference between them. We get an answer of 1,539,23 Newton. That is the force that is being exerted on that satellite A as it is circling the Earth at 25,000 kilometers. We may have time for this last one. Let's quickly do it. What distance should satellite B be at to experience the same force towards Earth as satellite A? Now, you can do this question two ways. You can either do it by explaining it, or you could do it by calculation to prove your explanation. So if we think about this carefully, satellite B is a lot heavier. Have a look there. So the mass of satellite A is 38,000 kilograms. The mass of B is 45,000 kilograms. So you can see the mass of B is bigger than the mass of A. Now, to experience the same force, so the force is staying the same, but the mass is changing, what has to happen to the distance between the Earth and the satellite? Well, if the mass is bigger, for the force to stay the same, the satellite actually has to be further away. The closer, the stronger the force, right? If the mass is the same. But now the mass is more. So that satellite has to be further away from Earth to experience exactly the same force. That would be a written explanation. So you would write that, and you could then use the formula of Newton, so Newton's universal gravitation. So you could use this formula, m1, m2, divided by r squared, to explain that if the force stays the same and the mass goes up of the satellite, then the radius needs to increase. So the distance from the Earth, center of the Earth, to the satellite needs to get bigger for that force to remain the same. Right, grade 11s, I hope that has helped you. Remember these questions, you just have to practice using your calculator as well. I hope to see you next time.